Really happy to be here. As Tom mentioned, this is a big week for space weather. There's about 300 people in town. They're down at the new Embassy Suites Hotel on Canyon and 28th, and it's all about space weather. So it's been a very busy week, but this is a really fun talk. I get to get technical talks there, and this is a more fun talk. I thought I'd start with the first question at the top, which is what is space weather? Since we have 300 people in town, what are they studying? What are they talking about? Why is this a thing, right? What I'll do is I'll do a historical overview of how we got to understand what space weather is and why we call it space weather before going into some of the impacts, which is the why should I care part, because it turns out that weather in space, as we call it, is really this very complex interaction between the sun and the Earth's magnetic field, the Earth's atmosphere, which can impact the technologies that we all kind of have come to depend on these days. So it'll be kind of a two-part talk. First with the history of space weather, how we got to know this term, space weather, and then why should you care about it. So launching right back in history to about the 18th century, this is a picture of people measuring the Earth with sticks. I kid you not, this was measuring the size of the degree in the northern latitudes. And as you can see above them, the artist which was accompanying this scientific expedition to measure the Earth with sticks saw the aurora and thought, well, I'd better put that in the picture. That's pretty incredible. So even back in 1736, they knew that the aurora was something really special. And it occurred primarily in the poles, you know, and people going up there saw this and thought, this is really weird. What is it? They had no idea. This is a book on meteorology. So by about 1850, 1860, it had been recognized as a phenomenon in the atmosphere, and they thought it was part of, you know, weather and the atmosphere, so it was part of meteorology back then. It had been seen, however, for hundreds of years, and this is a picture from 1580 in Augsburg, Germany, in which there was an obvious aurora in the sky, and it's a very bright one. It's obviously very unusual and unanticipated. Back then, these were omens of disaster or some sort of bad thing about to happen. I don't know German, and especially ancient German, but I think it says something basically like, this is a bad thing. So people were very afraid of aurora when they came down off of the poles and came into places like Germany. And throughout history, we have records going all the way back to ancient China and Japan of aurora coming far down south, and people just being shocked and awed by what this, you know, amazing light in the sky was. So really no idea what this was. Of course, today we have these beautiful pictures that people take up in the northern areas of incredible aurora with this beautiful green, the red. These are the stars in the background. This is a particularly amazing one. You're looking almost straight up into the aurora in Sweden. Looks like a dragon coming down out of the sky. This is even on a full moon night, as you can see. This is another shot looking straight down. This is from a satellite looking at an aurora over the United States at night. You can see sometimes they do come down into the United States, almost. This is over the South Pole, another satellite photo from the aurora in the South Pole, very detailed. This is the entire aurora seen from a satellite very far in orbit above the South Pole again. So you see it's this nice ring around the polar area. And this is a movie, a time-lapse movie taken in Norway by a photographer recently. I love this movie because it really shows how dynamic it is. These are not just still structures. They really move around a lot. They're fantastic. You see a shooting star going through there. And of course, when you're orbiting the Earth on the space station, you see these quite a bit. So this is back in 2012 from the space station. And you can see, again, the extremely dynamic structure of the aurora. But to get back to the 1850s, really, they had no idea what this was. It was really still a deep physical mystery as to what these lights in the sky were. They knew it wasn't sunlight. They knew it wasn't weather, really. But what was it? What they did know was that it was linked somehow to magnetic storms on the Earth. So what you're looking at here on the left is a trace of the Earth's magnetic field taken with a magnetometer instrument, shown on the right there, which is basically a magnet hanging on a thread, and they measure the magnet's deflection by the Earth's magnetic field. And they notice that sometimes these things kind of go crazy all of a sudden. They have a magnetic storm. They don't know what it is, but they know that when there is a magnetic storm, shown by these jagged traces here, they would often get reports from people in the north of aurora. And so by about 1852, Edward Sabine in England had already, this is data to the present day, but he'd already made a plot like this where on the bottom we see magnetic aurora sightings, magnetic storms and aurora sightings, and on the top, sunspots. So this is the number of sunspots on the sun going up and down every 11 years. We call it the solar cycle. So by 1852, they had this sort of hint that, well, when there's lots of sunspots, we get lots of aurora. So Edward Sabine and others were sort of putting forward this idea that maybe it has something to do with the sun. We're not sure. They also knew, though, again, that the sun was this regularly pulsing 11-year cycle. So here we have a plot, again, in modern times, but a plot of sunspot number as a function of time. And you can see about every 10 years you get a bunch of sunspots and then they go away. They come back and they come back. These are the sunspot cycle numbers, we call them. We are sitting here in cycle number 24, now down almost to the minimum of cycle 24. When there's lots of sunspots, we call that solar max. When there's very few, we call that solar min. We also know that sunspots during a cycle first appear at high latitudes, and then the subsequent sunspots get lower and lower. So we call it the butterfly diagram. So this was known back then. Everybody knew that the sun was doing this cyclical thing. Edward Sabine said, well, the Earth and the aurora are kind of following it. There must be a connection. Well, they couldn't really figure out any connection whatsoever of anything going on at the sun related to the aurora until one morning on September 1st in 1859 in Red Hill, Surrey, England, at this private observatory, Richard Carrington, shown here, observed a very large sunspot on the sun. And he was an amateur astronomer, but a very good one. Every single day he would draw sunspots on the sun and keep a very detailed record. And he saw these one day and he said, this is pretty significant. More significantly, on this particular day, all of a sudden, right here, 3 bright lights flashed out at him. And he'd never seen that before. So he ran out to get somebody to verify this. When they came back, they were gone. Luckily, another English astronomer, Richard Hodgson, had seen the same thing. So they had a verification. Something had happened on the sun. He was very excited about this, especially since at about the same time, as they later found out, on that magnetometer in Kew Observatory, London, there was this sudden dip right at the same time as he saw the flare. And then, about 17 and a half hours later, the magnetometers went crazy. There was the largest magnetic storm they'd ever seen. All of the traces went off scale. You had this gigantic magnetic storm which went on for quite a while. It was also detected all over the world. In fact, we've gone back now in time and we found that all the way over in Bombay, India, there was a magnetometer which registered a huge disturbance at the same time. Subsequently, aurora were seen in places that they'd never been reported before. This is Melbourne, Australia, which is far south, but it's very far from the southern pole of the aurora. So the aurora was coming way, way north for people in Australia. They'd never seen anything like this. In fact, here's a plot that's been constructed in historical times of where the aurora was seen. Now, how many people have seen the aurora here in Colorado? Not up north, but here in Colorado. So 2 or 3, yeah, it happens. It happens occasionally. So Colorado's here. So normally the aurora sits up here around the North Pole. In a big magnetic storm, it will come south. So sometimes we'll see it in Colorado. In 1859, during what they now call the Carrington event, they saw aurora down to El Salvador and Cuba. And again, in the South Pole, the aurora are coming away from the poles and coming towards the equator during this big storm. Here are the Australian sightings in Melbourne, all the way up here in Peru. Hawaii reported seeing very bright aurora. So this was unprecedented in modern times. In fact, this is one of my favorite quotes from this event. The red light was so vivid of the aurora that the roofs of the houses and the leaves of the trees at night appeared as if covered with blood. So this was down in San Salvador in 1859. They got this tremendously red sky all night. A lot of people thought there was a big fire somewhere. There was a lot of confusion. But over time they realized, no, that's the aurora. Importantly, as I'll point out later, there was also a big storm about 3 days earlier than this one. In fact, there was auroral sightings all the way down to San Salvador 3 days earlier. It just wasn't so spectacular. It didn't last as long. We'll come back to that a little bit later. So now in 1861, a compatriot of Carrington's, Balfour Stewart, at the observatory, the Kew Observatory, says, I think there might be something here. And he's very cautious. He said it would perhaps be wrong to consider this anything other than a casual coincidence. But since Sabine has already shown this relation between sunspots and magnetic disturbances, This is another great quote. "It is not impossible to suppose that in this case our luminary has been taken in the act." So he put this forward and said, yeah, maybe what Carrington saw had something to do with that giant storm. It's a very unusual flare. And no. George Airy, the Astronomer Royal, so when you have Royal on the end of your title, you're important, right? So the Astronomer Royal says, no, this is not right. No, he says his analysis of Sabine's data shows there's only a 6 or 6.5 year period in magnetic storms. Doesn't match sunspots. It's not the same. So he squashed it. Lord Kelvin, who was probably the most famous physicist of his time, at least in the West and the UK, went through this very detailed analysis in 1892 to show that, well, let's just assume that the sun caused this magnetic storm on the Earth. We know that the energy in the terrestrial magnetic storm has to be X, and he calculated that out. He said, assume that the sun is the source of this energy. He said, then assume that the sun emits this energy all through space. Right? This is the big mistake he made. He used bad physics, wrong physics. But he said if we assume the sun just spits out all this energy all through space, because the Earth is so tiny and so far away, there's no way that the sun could put out that much magnetic energy. So he magnetically proved that, no, it can't possibly be the sun. There's no way the sun could do that. They had no knowledge back then of what the sun really was or how anything could transmit magnetic field. He's famous for making bad predictions. This is another one of his quotes. So, if Lord Kelvin doesn't like your idea, don't worry about it. Just keep going. Just keep going. He was very wrong on that one. So it was only about 5 years later that J.J. Thomson in the lab discovered electrons. We didn't even know what electrons were back then until J.J. Thomson came along and said, hey, there's something that can transmit electricity across vacuum called electrons. So suddenly here's an idea, well, maybe there's a way to connect the sun to the Earth through electrons. We're not sure. 1900, Christian Birkeland in Sweden performed experiments in which he made kind of an Earth in vacuum, and he shot electrons at it, and he showed it made sort of this auroral glow around this magnetized sphere he called the terrella. These were very famous and beautiful experiments, and everybody thought, well, that's really interesting, but it has nothing to do with the sun, because obviously it's in a laboratory. So he was way ahead of his time. He really believed that the sun was the cause. He believed the sun was putting out electrons somehow and causing the aurora. It wasn't until 1908, 49 years after the Carrington event, that George Ellery Hale in the United States at Mount Wilson outside of Los Angeles, and you can still go and see this tower, it's still there up on Mount Wilson, measured for the first time using spectroscopy magnetic field on the sun. So he measured sunspots with spectroscopy and found there's evidence of magnetic field using the Zeeman effect, as it's called, to show that yes, the sun actually does have magnetic field. So this was a very key thing. This was sort of the birth of modern solar physics, if you will. Quantitative physical measurements applied to an astronomical object for the first time. So solar physics began to take off. The sun was magnetic, but there was no way that they thought the sun could possibly transmit that magnetism. They couldn't figure out how that could possibly happen. By the 20s, they knew that the sun, during eclipses, when you have a total solar eclipse, the moon gets in the way, you see this corona, this beautiful fanning out of plasma. They'd measured that plasma using spectroscopy again and found it's about 1 million degrees, which was not expected, but it was true. It's about 1 million degrees, this plasma, as it's now known to be, flowing out from the sun in this very distinct pattern, as you can see. So also by then they'd figured out that the sun is a very, very magnetic star. It has a very bipolar north-south magnetic field, which structures these coronal rays that you see at the eclipses. And they're a little bit more structured because sunspots and other things make it more than just a nice magnet, north-south magnet. So by the 20s, they knew that the sun was a very magnetic star. It was very active. They also knew, after Marconi, Guglielmo Marconi, had transmitted radio across the Atlantic for the first time and was continuing to do that on a regular basis. He also figured out that, when there's a lot of sunspots on the sun, we can't seem to get the radio signals across the Atlantic. And they didn't really know why, but they knew that there was a definite tie there. And in fact, they did atmospheric monitoring on top of the Eiffel Tower. So you could say back in 1928, they used to put out reports of how good is the radio signal to America. So you could say back in 1928, these were sort of the first space weather forecasters. They were trying to understand why is radio better or worse at any given time. And they were putting out reports. But still, they really didn't have a good idea of what was going on. In 1921, we may have had another Carrington event on the Earth. These are some really interesting headlines from various newspapers at the time. The tricky aurora snarls up the wires. There was a very, very large geomagnetic storm. Electrical disturbances, the worst ever known. Telegraph didn't work very well. They had a lot of disturbances in subway communication systems, train communication systems. They knew at this time, however, that the aurora borealis was something to do with this electrical disturbance on the ground. They also attributed it by this time to a sunspot. So the connection between sunspots to aurora to electrical disturbances on the ground was kind of pretty, at least correlationally established by 1921. They say here that there was an unusually large sunspot at the time on the sun that this occurred. And this event actually is being studied by several scientists here at Boulder, including Professor Dolores Knipp, who's actually in the audience tonight. So if you have questions about this event or some of the ones we'll talk about later, she's very knowledgeable on these historical large storms. So this one was really interesting. It also caused a lot of havoc in the power grid to New York. They had a lot of trouble balancing the power grid at the time to New York, even though it was a fairly primitive power grid at the time. And much like the Carrington event, there were auroral sightings very, very far south as Cuba. There's sightings in the daytime in Australia. I don't really understand that, but apparently people did report seeing aurora that might have been that bright at the time in Australia. So this was a very, very large event. It did spur some interest again in this entire idea of how is the sun doing this? There still was no real direct connection that they could make physically at the time. Another related activity at the time is Edward Appleton in the 1920s, 1924, discovered / formulated the idea of an ionosphere, the sort of electrically charged layer in the Earth's atmosphere which allows radio waves, like Marconi's radio waves, to bounce off the ionosphere and get over the oceans. So by this time we knew that the sun was causing, through its ultraviolet rays, was causing the ionization in the atmosphere, allowing this electrical layer to form and bounce radio waves off. That was a key part of the clue. In 1933, Sidney Chapman, who was a very famous solar physicist and geomagnetic geophysicist, and Bartels formulated the idea that maybe there is something, we don't know how, but maybe there's some big magnetic pulse coming from the sun, let's just say. And they formulated the idea that, well, if that happens, the Earth's magnetic field, which is shown here, sitting out in space, is going to get squashed. And that squashing is going to cause this sort of havoc that we think is a geomagnetic storm. And they were right, but at the time, again, it was like, well, that's nice, Sidney, but how is that happening? What's coming from the sun that's causing that? There's no real way to prove this. It's just a nice theory. Moving into the war years, this is a nice local story. This is Walter and Janet Roberts up at the Climax Solar Observatory in Leadville, Colorado. And what they were doing is he was using this observatory here and a coronagraph instrument, which looks at the corona of the sun, makes an artificial eclipse, to monitor the sun for solar flares for the Army, to tell them when it was going to be more difficult or less difficult to radio over to Europe. With long-range radio. So there's Walt and Janet up at Climax trying to ski up to their house probably. Obviously it's quite snowy up at 11,000 feet. The interesting thing about Walt Roberts is after he came down from Leadville and the observatory, he came to Boulder and brought solar physics to Boulder in the University of Colorado and formed eventually the National Center for Atmospheric Research and created the MESA Lab. So there's Walt Roberts in 1967 after creating the MESA Lab and NCAR, which his interest in the atmosphere, he's a solar physicist interested in flares, his interest in weather was spurred by the fact he thought maybe the sun is also affecting weather. He's in that sense a little bit off because there's no real transitory effects of weather by the sun. The long-term climate effects, of course, are there, but anyway, he formed this entire weather center that we now know as a world-famous center. So a little bit of local color there. This is one of the most famous movies ever taken by Walt Roberts at Climax Observatory, the largest solar eruption still to this day ever recorded. Seen here, that's the size of the Earth for comparison. So you're seeing this gigantic eruption from the sun. Now, this was obviously something that Walt Roberts was thinking, there's a giant cloud of something erupting from the sun. Maybe that's what's causing, this transmission of magnetic field and et cetera from the sun. But a lot of people said, well, look, it's not, we're taking this picture from the Earth, it's going that way, so it doesn't look like it's going to hit the Earth. I don't know what you're talking about. So there was still not a real firm idea that something from the sun could actually come to the Earth and affect the Earth, although they were now seeing things like this and saying, obviously the sun is not just a static star, it's putting out a lot of interesting things. Also around this time, 1946, Scott Forbush was reporting, he was working with ground level neutron measurements specifically for the atomic bomb efforts and trying to detect atomic weapons testing. So they had all these monitors all over the Earth to detect neutrons from atomic explosions. But he noticed, being a good scientist at the Terrestrial Magnetism Center at Carnegie, that there were sometimes signals picked up after large-scale solar flares. And so he posited what they called back then cosmic rays coming down from the sun, possibly due to charged particles from the sun. So this was the first idea that not only was the sun maybe throwing off some plasma in these giant eruptions that Walt Roberts was seeing, but it might also be putting out charged particles somehow. And when they hit the atmosphere, they turn into these big air showers, including neutrons, which come down to the ground and are sometimes detected on the ground by the neutron detectors. So the pieces are starting to come together. There's obviously things happening on the sun that look like they could affect the Earth. Julius Bartels in 1949 formulated the idea that there's a planetary magnetic index we can calculate to show how disturbed the magnetic field is of the Earth, and he plotted this at times, and you see at times it gets very disturbed and then it's quiet. So when there's these large notes, as he called it, this was the music of the magnetic field, as he called it, there's big disturbances in the magnetic field. So he made this index, which kind of goes from 0 to 9 for how disturbed is the magnetic field of the Earth. And we still use his index today to describe magnetic storms in terms of the KP index, as we call it. And he also wrote one of the first papers, if not the first paper, looking back at the Carrington event and saying, gee, in 1859, I'm finding a lot of interesting information on this event that may have something to do with magnetic field disturbances that was really big in 1859. So he kind of started this historical look back at the big event in 1859. By the 1950s, sunspots were being tracked on a daily basis. This is now at the Inter-Service Radio Propagation Lab, which was then called the National Bureau of Standards in Boulder, Colorado. So this is today, oops, I thought there was something today, going back. Today, this is what we call NOAA, and we call this the Space Weather Prediction Center here in Boulder, Colorado. But in the 1950s, this was the sunspot tracking of the time, by hand on a blackboard. In 1958, as many people know, especially here at LASP, James Van Allen, who was the thesis advisor of Dan Baker, the current director of LASP, discovered, using Wernher von Braun's rocket and a custom-designed satellite in 1958 on the Explorer 1 flight, that there were such things as radiation belts above the Earth, and we now call them the Van Allen radiation belts. This is a modern measurement / animation of these bands of radiation. They're kind of like big donuts that circle the Earth, and they're full of charged particles, protons, electrons, very high energy. And the conclusion upon a few of these flights after Van Allen had sent up a few of these is that space is radioactive. That was kind of unexpected. And people thought it was just maybe a vacuum, there was nothing at all up there. In fact, it was extremely radioactive, and it's quite dangerous to be stuck in one of those belts when there's a lot of activity on them. Again, that was a sort of a mystery of where is this radioactivity coming from? Why is there a band of radioactivity around the sun, or around the Earth? In 1958, Eugene Parker at the University of Chicago theorized that, well, we've got this million-degree plasma sitting around the sun. It's going out into a vacuum. Perhaps it's actually creating a solar wind. This was an idea that was put forward earlier by people like Bierman and Chapman, but he really put it together, did the mathematics, purely mathematical theory, and showed that, yeah, we should expect to have a wind coming off of the sun, throwing out this plasma, which is basically electrons and protons, all the time. Everybody, in fact, he had a really hard time getting this paper published. It was rejected 3 times. It was finally the editor of the Astrophysical Journal, Chandrasekhar, who was his thesis advisor, just said, to hell with it, I'm publishing it. And he put it in the journal and said, there you go. And even though it had been thoroughly rejected, he published it. And luckily for us, he published it because it turned out to be right. In 1962, Marcia Neugebauer, who was on the Mariner spacecraft project, analyzed the energetic charged particle sensors on that satellite and found that, as you can see in the highlighted section here, there was always a measurable flow of plasma from the direction of the sun, and the plasma velocity was 400 to 700 kilometers per second. So she verified the solar wind. And at that point, people sort of, I guess, had to eat their hats and say sorry to Parker, because he got it right. So by this time, we knew that the Earth is surrounded by what we call the magnetosphere. The Earth is a magnetic planet, of course. It has its own magnetic field, but there's now, we know, a solar wind constantly pushing that magnetic field back into this sort of tadpole-shaped magnetosphere, as we call it. The Van Allen radiation belts sort of sit here inside, comfortably inside the magnetosphere. There's a shock wave here out in front of the Earth, several, probably 10 Earth radii, 20 Earth radii, something like that, where that supersonic solar wind hits it and goes around it. So there's a constant source of shock wave energy here. And then you see this magnetotail, as we call it, this magnetic field being drawn out as the solar wind sort of sweeps back the Earth's magnetic field lines. So this was all sort of a picture, a nice picture was coming together of the Earth sitting out in a constant stream of solar plasma, shown here in these streaks going by, and you can see they're being deflected by the magnetic field. And when there's a more dense pulse of solar wind like that, you can still see we're sort of shielded by that magnetic field of the Earth. So by the 60s, this was a pretty clear picture. We knew that the magnetosphere was there, it was shielding us from the solar wind. This shows you the Earth's magnetic field lines in a cartoon variety, providing that cocoon of protection from the solar wind. As a side note, we now know that Mars is not so lucky. Mars does not have a magnetic field. So the planet literally sits out in the solar wind, and you can see here the bow shock is right up against the planet. And this is findings that have been really solidified by the recent last mission, MAVEN, which is now orbiting Mars and taking these measurements. And I love this movie because what we're going to see now is the idea, pretty much proven now by the MAVEN measurements, that because Mars doesn't have a magnetic field, the solar wind has swept away its atmosphere. We believe it used to have an atmosphere, perhaps a primordial atmosphere, but the solar wind over time has just swept away the Martian atmosphere. And so this movie, including the very sad music, dramatizes the fact that without a magnetic field, you have no atmosphere, and therefore you probably have no life. This is the ion flow measured by MAVEN. It's not symmetric. It's interesting. There's a big fountain over the North Pole. But they're still measuring stuff stripping off the planet's very thin atmosphere at this point. It's a very interesting planet otherwise, but no magnetic field, no atmosphere. So I'm going to choose 1963 as an interesting date to just call a summary at this point of what they knew, what we knew at the time about what space weather was. We knew that the sun was a magnetic star by this time. We had this 11-year sunspot peak, and in fact we know that the poles of the sun flip every 11 years, so it's really a 22-year cycle. The color here is a whole magnetic cycle of 22 years followed by another one where the pole of the sun is flipping back and forth. We know that the sun's corona is 1,000,000 degrees. It flows out into space in the form of this magnetic plasma solar wind. Sunspots are very strong magnetic fields, and we know they occasionally flare, as it was called back then. They didn't know what that was really, but they knew that there was these giant, bright periods of flaring. And right after that, the ionosphere, this electrically charged layer above the upper atmosphere of the Earth, kind of gets perturbed, radio signals go crazy. That was all pretty well known. Sometimes after really large flares, they would detect these neutrons on the ground and say, wow, there must be some charged particles coming off the sun and hitting the Earth's atmosphere, creating neutrons. They called them then, this is now, we still call them solar energetic particles, this radiation being thrown off the sun somehow. We know that the Earth is surrounded by this magnetic cocoon called the magnetosphere, interacting with stuff. And we know that space is radioactive. The magnetosphere forms these rings of charged particles called the Van Allen radiation belts. And that once in a while, geomagnetic storms are correlated with these big flares they see on the sun. It's always about 24 to 48 hours later, though, so it's not like the flare goes off and you get a magnetic storm. It's the flare goes off, and then you wait and you wait and you wait and you wait, and then you get a magnetic storm. So there was still this kind of question, like, what is that delay? What is actually causing the magnetic storm if it's not the flare itself? Starting in about 1965, they really started to watch the sun on a daily basis, primarily for the space program. This is the Gemini 7 mission up in orbit, and this was in Boulder, Colorado, what was then called the ESA, or the progenitor of NOAA. But here in Boulder, the Space Disturbance Forecast Center started putting out very detailed daily reports of what the sun was doing in order for the astronauts to know if there was a big flare, maybe these radiation particles were going to be coming, and they should probably know if they're getting fried. Nothing you can do about it, but you might as well know, right? These are sunspot drawings done by hand, still to this day done by hand, up at Swipsey, showing the activity on the sun. And as I mentioned here, we're still doing this at the NOAA Space Weather Prediction Center. So Boulder still is the center of space weather prediction and forecasting, at least for the civilians. The military does their own in Offutt, Nebraska. This is the key observation. In 1969, radio observations of the sun for the first time saw plasma blobs coming off the sun in a direction more or less towards the Earth. So no more big prominences going off into space that doesn't matter. This was stuff that appeared to be coming towards us. In 1971, they made artificial eclipses on some satellites. This was the Orbiting Solar Observatory, and they observed some more plasma coming off the sun in directions that seemed relevant to the Earth. In fact, they called these things coronal mass ejections, or CMEs, and we still call them that to this day, to describe these plasma blobs coming off of the sun at very high rates. But it's very interesting, if you go back in time, this is a picture from an 1860 eclipse, hand-drawn, and there seems to be this very strange blob of material sitting off the rim of the sun. So we think that perhaps people had been seeing these things earlier, but without the aids of photography or movies that they could actually transmit the data from. All we have are these very sort of enigmatic drawings. In 1973, we launched Skylab with one of the last Apollo rockets, and this entire instrument package here is devoted to looking at the sun. And on board there was an X-ray telescope that showed for the first time there are these big gaps in the X-ray emission from the sun, and they called these coronal holes, and they really didn't know what they were. But they did notice that every 27 days, the sun rotates about every 27 days on its axis. Whenever these things came by the Earth, they would get a disturbance in the ionosphere and a geomagnetic storm. So there was some idea that something's coming off of the sun in these coronal holes that's causing geomagnetic storming. In fact, this is an artificial eclipse, again, formed at Skylab, showing one of these big blobs of plasma coming off as well, CMEs. This is a data taken by a telescope designed and built here in Boulder by the High Altitude Observatory, the SO52 coronagraph it's called. And this was taken a few weeks back. You can go up to the third floor of HAO and see this instrument right there. That's an engineering model of what flew on Skylab to take these pictures. So by the 80s, they were launching satellites, large satellites to measure things like radiation in space in detail. And you can see here that the sunspot cycle below, as the sunspots wax and wane, sort of anti-correlates with the base of this. They figured out that what they're looking at there is the galactic cosmic rays, the constant rain of radiation from outer space, way far interplanetary, intergalactic outer space. As the sunspots maximize, the sun's magnetic field swells up and sort of shields us from the galactic cosmic rays. However, when there are lots of sunspots, you get lots of flares and these explosions, which they didn't quite understand at the time, but they did know that you would then get these big spikes of protons. So these were called, again, the solar energetic particle events. And I always like to compare this to a garbage can. I don't know, to me it just looks like a garbage can, so every time I see it, I see Oscar the Grouch. Where'd he go? There he is. The IMP satellites just remind me of Oscar. Anyway, by 1991, they'd launched very advanced X-ray telescopes. This is the Yoko telescope, a Japanese telescope with a Lockheed Martin telescope and camera on board. This is the sun in X-rays, and you can see when you look at the sun in X-rays, you really begin to see these sunspots throwing off a lot of energy and flaring. And at this time, it became pretty clear that it's not just sunspots alone, but it's somehow the magnetic field above the sunspots that's causing these eruptions. And in fact, they found, looking at Yoko, when you look at a sunspot in X-rays before the eruption, you often see an S-shaped curvature of these twisted magnetic fields, if you will, as they thought they were. And then after the eruption, that S is gone. So there's something on the sun that was twisting up the magnetic field, turning it into these sort of S-shaped forms before it erupted and caused these big X-ray flares. In about the 1990s, people said, well, wait a minute, we want to look at the sun all the time. It's hard to do that from Earth because the Earth rotates, so you get these 12-hour dark times where you don't get to see the sun. If you put something in orbit around the Earth, the moon gets in the way, the Earth gets in the way. So why don't we go to this very special place called L1, or the Lagrangian point 1, which is the gravitational balance point between the Earth and the sun. And you can put stuff there, and it rotates with the Earth around the sun, and you can just point it at the sun, and you have 24/7, 365 views of the sun. So people started putting things out there. It's also a very good place to look at the Earth. So this is a recent photograph of the 21 August 2017 Great American Eclipse, taken from Al Gore's Triana satellite, which was launched by NOAA and renamed Discover in 2015. But this has both sun-facing instruments and Earth-facing instruments. And of course, if you look back at the Earth from L1, you see a completely sunlit Earth all the time. So it's a great place to look at the Earth. And they get these fantastic movies from there. But in 1995, going back to that time, a very significant satellite was launched. This is called the Solar and Heliosphere Observatory. It was a joint project between the European Space Agency and NASA, and it was instrumented with lots of solar pointing telescopes and solar wind measurement instruments. For the first time, we were now measuring the sun from space constantly. No interruptions, no eclipses, no day-night cycles. This is when solar physics and the understanding of space weather really took off, because we had the instrumentation to do a constant monitoring of the sun. So SOHO made movies like this. This is measuring the magnetic field like Hale did back in 1908. Now in 1995, this is the magnetic field measurements we're making of the sun from space. And you can see sunspots are these magnetic structures. Magnetic field always comes in a plus and a minus polarity. So you see black and white polarity is always together. So they're like giant magnetic storms bubbling up into the sun. But the sun is also very significantly completely peppered with magnetic field all over the place. So it's not just the sunspots. It's a very complex star that creates its own magnetic field in ways that we don't quite understand yet. It's basically a dynamo process of some kind with the plasma churning around in a very special way. But that's still a very active field of investigation. Is why does the sun have a magnetic field like this? Why does it peak and wane every 11 years? This is the X-ray telescope, or in this case, extreme ultraviolet telescope on SOHO, and we could see for the first time these giant flares in great detail using this telescope. So we saw sunspots with their magnetic field would rotate across the disk. The more magnetic field they had in the sunspots, the more apt they were to cause these giant flares. And then finally, SOHO included its own coronagraph, where you see the disk around the sun blocking out the sun's light, so you can see the corona and these coronal mass ejections coming off all the time. So finally, we had something in space looking at the full gamut of solar activity all the time. And CMEs went from being this occasional mystery of what was it, to this very obvious, very common explosion of plasma from the sun in all directions at all times. Also in about 1997, we put a very special satellite out at L1, same thing, pointing at the sun all the time, measuring the solar wind constantly. So we always had a measurement of the plasma flowing towards the Earth. Because if something comes to L1, it's going to come to the Earth. It's not going to miss once it gets to L1, right? This was called the ACE spacecraft. The very special thing about this was NOAA paid for a real-time constant downlink of data, so that we always had data coming down from that satellite. We didn't have to wait for it to dump data occasionally. So it really became the first real-time constant solar wind space weather monitoring satellite. SOHO dumps data every once in a while, so you have to wait sometimes for SOHO to get data down. Moving forward, NOAA also put solar instrumentation on top of their weather satellites. So the weather satellite's mostly looking down at Earth, but on the solar panel you've got a sun-facing X-ray telescope. And they started defining solar flares for us. So we're starting to quantify solar flares. We call them Originally, it was called, in terms of the size of these particular X-rays, between 1 and 8 angstroms, very short wavelengths of light. They classified them in terms of A, B, C, M, and X in logarithmic scale here. So originally C, M, and X meant common, medium, and extreme. And then I guess they went back and said, well, we need A and B too, because there were small ones. But anyway, you can see here that when there's lots of sunspots, it's very exciting near a solar max. You get these big giant flares, sometimes up into the extreme range. However, this is very recently, a few days back, it's very boring when you're near solar minimum. There's no sunspots. You get no flares, nothing. All the X-rays just sit there. That's the way the cycle goes. In 2000, there was an image, a satellite called IMAGE, which looked at the aurora constantly, all the time. So that's the satellite that took this very famous picture of the full aurora. So we really got to see when the sun did something and one of these coronal mass ejections came off and hit the Earth, we saw the aurora light up like this. So by the 2000s, we're now in the position to really make a summary of what is space weather. This sort of wraps up the first part of the talk. No, only an hour and 14 minutes into it. Sorry about that. Bear with me a little bit. We'll go through the summary pretty quickly here. We now know that it's not flares, it's not solar wind, it's solar magnetic eruptions from sunspots, which trigger these giant sequence of events. Namely, you get a giant flare and photons coming off the sun, followed by a coronal mass ejection, which explodes plasma out into space, followed by these energetic particles, which sometimes come streaming up with the CME. It's accelerated by the shock wave in front of the CME. 14 to 48 hours later, this is why there's a delay, that plasma kind of rumbles through space. The CME takes time to get to Earth. It's not going at the speed of light like the flare. If that CME collides with the Earth, that's what causes the magnetic field of the Earth to be perturbed and cause a giant geomagnetic storm. So it's really the CME causing the geomagnetic storm. When that happens, you get magnetic reconnection, as it's called. The magnetic field of the Earth gets so perturbed it reconnects with itself and causes all kinds of particle acceleration locally in the magnetosphere, and particularly in the tail. That throws back particles into the northern regions, and you get the aurora. And then less severe storms are caused sometimes by those coronal holes as they spit out high-speed solar wind. And even less minor space weather can be caused by thunderstorms in the troposphere, causing waves to come up into the ionosphere. So space weather is now understood to be an entire system, really from the ground to the sun, of the atmosphere and the magnetic field interacting in this very complex way. And even weather can now, we know, perturb the ionosphere. So for those who don't like words so much, but like
when the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
So voila, by the 2000s, roughly, we know now how the Carrington event and the giant aurora are formed. They are essentially magnetic eruptions from the sun interacting with the Earth system. It's not just the Earth, as we know, though. Mars, as I showed, also is subject to these things. All the planets are bathed in the sun's atmosphere at all times, and when it has these magnetic eruptions, if a planet is in the way, it's gonna have its own space weather. So, if you'll bear with me for maybe another 15 minutes, I'll go through some of the why should we care part, because I've just gone through the history of what space weather is, sort of the physics of space weather, but I'd like to get into a little bit about what happens to the technological systems we have here on the Earth and why we need to forecast these and understand better how to forecast these events in order to protect a lot of the systems we have. So I'm going to skip the time scales. We know there's lots of time scales here. It's a big sun to mud problem. This is interesting to show, though. This is the sun erupting a CME. These are not small structures, so already by the time it's 40 or 50 solar radii out, it's much, much larger than the sun itself. And this is going to stop when it gets to about 150 or 200 radii, rather, where the Earth sits. So now we're out where the Earth is, And now we're zooming into the Earth. So that's the size of the Earth relative to CME. So you see, we're not just dealing with a small piece of plasma coming off here. We're dealing with things that are 100 to 200 times the size of the sun coming off, and we just get hit by a piece of it. Sometimes we get hit by more or less of it, and that determines the strength of the storm, really. And one of the key things in trying to forecast these things is trying to see how much of that CME are we going to catch here at our position at the Earth. So why should I care? We'll go through quickly a rundown of these sort of three big things that happen. The first thing that happens when you get one of these magnetic eruptions is you get a flare, a giant amount of X-ray photons coming off the sun at the speed of light. We've known since the 20s that this also puts out radio noise. So the sun not only puts out photons in terms of light and X-rays, but it puts out tons of radio noise. If that radio noise happens to be at radar or GPS frequencies, those systems are going to be impacted. Also, it ionizes the atmosphere, as we know, creates ionospheric disturbances, and high-frequency radio that goes over the over the horizon gets perturbed. It also causes prompt heating of the upper atmosphere, and the upper atmosphere will swell up. And if there's satellites, which are actually flying through the atmosphere in low Earth orbit, those satellites will feel drag, and they'll start going slower and fall down. And so satellites will actually feel the atmosphere expansion during space weather due to flaring. The radiation storms that are caused by these giant explosions accelerating particles in front of them cause all kinds of damage to satellite electronics and solar arrays. Just like we know, radiation poisoning of astronauts, radiation's bad stuff. It's really bad for humans, it's bad for electronics, it does wreaks all kinds of havoc. In a really bad storm, it'll come all the way down into the stratosphere and endanger airline crews and passengers. And then finally, geomagnetic storms, the big third piece of the puzzle once the plasma cloud hits the Earth. That causes lots of interesting effects. These big magnetic field changes generate electrical currents in the atmosphere. So we have a giant current going around the ionosphere we call the ring current. At the same time, the Earth's crust is also a conductor of electricity. And when you change the magnetic field in a conductor, you get electrical current. So you get giant currents in the ground during these geomagnetic storms. And that's what wreaked havoc with the power grid in New York and the telegraph system in the Carrington event and in New York. There's electricity coming up from the ground into the power system and the telegraph system. And electricity is not supposed to be coming up from the ground. It's just, that's supposed to be the ground where you put stuff in. So when stuff comes out, your electrical systems get very unstable. And then finally, we know that the magnetic reconnection, the magnetosphere back in the tail, is what causes the aurora by snapping back those particles into the polar regions and causing the actual glow of the aurora. So as I mentioned in the abstract of this talk, if we didn't have any of this technology, then space weather would be relatively harmless, except for the very, very rare events where radiation can reach the ground. It just creates these fantastic aurora. So who cares? Well, we care today because primarily, if you look at GPS in particular, we're extremely reliant on GPS for lots of different things. And I'll have a slide on that in a bit. NOAA has also quantified all of these things in these scales, so we now have nice 1 to 5 minor to extreme scales that we talk about for all of these events. So we can quantify an event in terms of the scales. That's very handy. The most recent very extreme event we had was back in 2003, where this very nasty looking sunspot group wreaked havoc. And I'll go through a little bit of what that did. There's the magnetic field. Whenever you see that kind of complexity, you know that's going to be nasty. This is a movie of the sunspot group as it went across the disk, flaring. There's a very large flare. You see all that snow on the detector? That's the radiation blasted out from the sun in front of the shock wave, hitting the camera and causing the camera to record the radiation, the protons and the electrons hitting it. So luckily these things are hardened. They survive in space even though they're being irradiated at this rate. This would probably be very unhealthy for a human being to be sitting in the middle of. This is the X-ray trace I showed. In 5 days, in October, November of 2003, there were 5 or 6 major extreme flares, including the largest flare ever recorded in GOES X-rays. This is a picture of it. It was right at the limb of the sun, so the explosion that it created went straight out and missed Earth. So we didn't get hit by the CME that came with this explosion. And that's probably a good thing, because that probably would have been a Carrington-like event. This is a view of some of the CMEs coming off at the time. You can see the flares happening in the small image of the sun there. So this was an extremely active time. There is another radiation hit on this particular camera. That happens to be Venus going by in the background. But this was an incredible series of events over a day. This is the radiation storm that accompanied the major first flare. And you can see it got up to above an S4, so almost the highest levels of radiation ever measured in this one event. And it wreaked a lot of havoc. It caused a geomagnetic storm, which in the Bartle scale of KP 1 to 9 reached the 9 scale. And that continued over 3 days, October, November. If you measure the ring current in this, what we call the DST plot, when these things go down, that's bad. And this is a superstorm level of a minus 300, minus 400 DST index, as we call it. Here is the Carrington event, however. So as bad as this was in 2003, we still think that we still have a long way to go in terms of geomagnetic storming before we get to anything like they saw in 1859. And it's good to keep in mind that back in 1859, they had only telegraph systems. And that was affected quite a bit, but they were recovered pretty quickly. This was the aurora over Houston, Texas in 2003. So the aurora, that blood red aurora, came down as far as Houston at that time. So 2003 was kind of a dress rehearsal, if you will, for a Carrington-like event. There were lots of impacts. The GPS-based wide area augmentation system used by airlines for precision landing was put out of it was unavailable for about 8 hours. It wasn't broken, but it was unusable because it was fluctuating so much. The radiation storm levels were so high that there were astronauts on the space station at the time. They were told to shelter in place for about 8 to 10 hours. There's not a lot of shelter on the space station either, so you got to be a little bit nervous when they tell you to go hide, behind aluminum, right? But there's some water tanks. They try to put them in the middle of water tanks and keep them safe there. But that's not a fun place to be for 10 hours, right? Stuck between water tanks. There were a lot of satellite anomalies. SOHO itself was inoperable for several hours. So even the satellite monitoring the sun at the time was put out of business by this flare for some time, these events. Airlines took unprecedented actions at the time because they knew there was going to be a lot of radiation from the aurora coming down into those polar regions. And at that time, the polar routes had been opened up. They were flying over the poles, but in this case, they deviated around them. And when you deviate airline routes, it costs a lot, $10,000 to $100,000 per flight. Energetic protons and this radiation spray you saw on those cameras actually caused, or they think it anyway, because the satellite died shortly thereafter, but it was suspected to have caused the loss of the $640 million, aptly named, I might add, Adios satellite. The Adios was gone, and it took with it the $150 million NASA Seawinds instrument, so that was an immediate and total loss due to that solar storm. And then finally, in Sweden, they had about a 3-hour blackout caused by these geomagnetically induced currents coming up again from the ground, getting into the power grid and destabilizing the power grid. So there's nothing they could do, and they lost power for about 3 hours. So I won't go into the physics of the ionosphere so much. This is a nice view of seeing a solar flare cause a big absorption of radio waves on the sunlit side of the Earth. So when you're facing the sun and it has a flare, this whole region is now not really usable by airlines or anybody trying to do over-the-horizon radio. That's a nice view of an impact of the immediate impact of the flare. As I mentioned, the GPS system is now really relied upon a lot, not only for positioning. We're most familiar with it probably from our maps that we have on our phones now, but probably more importantly, it's used for precision timing in all sorts of things. And one of the things it's used for precision timing in is 40% of all trades on Wall Street are timed with GPS. And we've talked to them and said, do you know that you're using a system that could be taken out? And they're like, yeah, it doesn't matter. they don't care. Right? Some people might say it'd be a good thing if they got taken out. So this is another example of that radio noise. These are GPS receivers all looking green saying, yeah, we're getting good signal from GPS, everything's fine. And then blammo, a solar flare goes off, and suddenly for about 10 minutes, GPS is unusable by all of those red dots. It's too noisy. The sun is just swamping the signal. So there's no GPS there. Your autonomous vehicle running on GPS or autonomous landing system trying to land on the center line of a foggy runway is all of a sudden going to have a lot of trouble right there. So this is one of these impacts. And in fact, this is the wide area augmentation system of the FAA. In that 2003 storm, you can see where it's green and blue. It's okay, you can use it. But all of a sudden, the geomagnetic storm really kicked up. And pretty much the entire continental U.S. is now no longer usable by that FAA system. Similarly, flights going from New York to Hong Kong, as I mentioned, over the poles, once you get up over 82 degrees, you can't use satellite communications anymore because you can't see the satellites down on the equator, the geosynchronous equator. So once you're above 82 degrees, the only way you can communicate with the ground is through high-frequency radio. So if there's a big flare at the time, you can't communicate at all. And it's a big deal when airlines all of a sudden don't report in as they're supposed to every 30 minutes on their flight. And so that's why they have to reroute around that 82-degree circle, and that costs a lot of fuel to do that. One of the scariest things that has just come up, again because of Dolores and her historical sleuthing, was in 1967. We didn't know about this until recently because it was all highly classified, but at the time we had these giant radars looking out for missile attacks coming over the poles from Russia. And all of a sudden, on 23 May of 1967, these radars started going crazy. They were getting swamped by noise. And of course, the military guys get all hyped up and they think it's an attack. They thought it was a Russian jamming operation prior to a missile launch. And so there was a real panic going on until they luckily called down to, as you can see, this is 67, so a few years after regular solar and space weather forecasts had been started up here in Boulder. They got a hold of people at the Air Force, got a hold of people at Boulder, who said, no, hold on, there's just been a giant solar flare, and that noise you're getting on your radar is actually from the sun. And so they backed way down. I mean, they were on full alert for a nuclear war in 1967 at this point. But luckily, there were some space weather forecasters who were able to say, it's the sun, don't worry about it. They were correct. Another very recent example of this was in 2015. The Swedish Air Traffic Center all of a sudden was completely blinded. They couldn't see any of the planes out in the direction of the sun at sunset. This was in November, so the sun was low in the sky, and there was a solar flare that went off and created, it wasn't that big a flare, it was really just an M flare, medium-sized flare, but it, for whatever reason, had a very strong burst of radio energy right down the barrel of these radars. And so they lost track of all the planes coming in along the solar route. They had to sort of shut down the airspace, and it was a big deal at the time. It took them quite a while to figure out that the flare had done this. Nobody thought a flare could really do that, but that was indeed another solar flare. I'll just go quickly through the radiation effects on satellites. This is another event that Dolores is sleuthing out and has written an article on. In 1972, we had a giant, you can see the size of the sunspot is immense. There was a huge flare on August 3rd of 1972, and the CME that was thrown off the sun at that time was the fastest on record, significantly faster than the Carrington event. It got here in 14 and a half hours instead of 17. That's a speed of 6,375 miles an hour. When it got here, because the magnetic field wasn't really aligned right to wreak total havoc with the Earth, the geomagnetic storm wasn't as intense as it might have been in a true Carrington event. It did create some problems. What was really bad in this one was the solar energetic particle event. It was the biggest solar energetic particle event in the modern age. It blasted the solar arrays of the Intelsat, ComSat, and many other ComSats, so that in 10 minutes they lost 5% of their solar power, in about 30 minutes, which was equivalent to being on orbit for 2 years. So all of a sudden, all these satellites lost 2 years of orbital lifetime. They also subsequent analysis has shown that had the Apollo 17 astronauts been on their way to the moon, as they were in December of 1972, not August, but December, but had they been outside the magnetosphere, that protective cocoon at this time, they would have definitely been extremely radiation sickened and perhaps even killed by this radiation event. So this was a really big radiation event, the likes of which we haven't seen. And as we know, we have a lot more in orbit now since 1972. We've got many, many more assets up there. We're much more reliant on things than we were then. We also know that as we see neutrons on the ground, that means there's neutrons on the air. So again, the airplanes are going to be rerouting to get away from that. And also, this was a very interesting event. In a relatively minor geomagnetic storm, you still get lots of electrons bouncing around the magnetosphere. And in 2010, there was this giant Galaxy 15 communication satellite, which sits out there at geosynchronous orbit, all of a sudden was zapped by what they think was a big cloud of electrons snapping back from the tail. And it was still going and it was still transmitting, but they couldn't talk to it and they couldn't command it. So it started to drift in its orbit. And they called it the zombie satellite because it just sat there and drifted. And it was actually it was to the point where they thought it was going to drift in front of other ComSats and interfere with them, so they actually had to move it out of the way. It took them an entire year to get that satellite back into operation. They finally did, but it was a big problem at the time, and it was a pretty minor storm, but this just shows you can get a lot of severe radiation up in the magnetosphere, even in a minor geomagnetic storm. The power grid, of course, is a concern. If we get these very, very large currents again, you can get effects on the what's shown here, the extreme high voltage power grid of the United States. And in 1989, in Quebec, there was in fact an entire blackout of the Quebec province. About 6 million people were in the dark. It took 90 seconds for the geomagnetic storm to cause this blackout, and it took about 9 hours to recover the power. It also damaged severely a transformer. Oops. In New Jersey, burned out. And these are the size of these transformers. They're sort of house-sized, $30 million pieces of equipment. You don't just pop these in and out. It takes months to replace these, realistically. And so that was a very, very severe event. One of the most severe geomagnetic storms in history, actually. So I'll just skip through some more of this. This is why satellites in orbit need to know what's happening to the atmosphere at all times.
I heard about the potential collision on Thursday evening. I thought, oh, that's odd. But let's not panic just yet. And then we got an update on Friday, and it looks worse. Oh, my heart sank. So we then continued over the weekend, and it just didn't get better.
There are all kinds of things orbiting the Earth. Obviously, the active spacecraft that we're still using, but also expired spacecraft, many of them still on orbit. And then there are old parts, and then real debris down to flexpaint. If you see a piece of debris far enough in advance, you can decide to alter your orbit to make sure that your orbit and its orbit don't intersect and there isn't a collision.
Fermi is a special kind of telescope designed to make observations of the universe in the highest energy form of light, in gamma rays. Fermi sees gamma rays from supermassive black holes, gamma rays from the remnants of stars that have exploded at the end of their life. But we also see gamma rays from flares from the sun. And we get a very different picture, and thus a much deeper understanding of what you're looking at.
Late March of 2012, we got a call from the Department of Defense. There was a defunct Russian satellite in an orbit that would intersect Fermi's orbit in about a week. It isn't that they knew they were going to hit, it was that they didn't know that they weren't going to hit. So that's something we had to be concerned about.
And that's because the atmosphere is
Those two
fluctuating so much,
spacecraft
we don't really
same
know where
space
those are.
within 30 milliseconds of each other. That's why this is so scary.
Wow.
These are objects several tons each, as wide as a small airplane, traveling 20 times faster than a bullet. The Fermi mission would be over. The spacecraft almost certainly would not survive that. The basics of the collision avoidance maneuver is we just use our thrusters to alter our orbit a slight amount, just to provide a little bit of separation between ourselves and the other piece of space debris.
We hadn't ever used the propulsion system before. And using something for the first time was going to be a major decision. And we had to decide, of the two disasters that could happen, a collision with another satellite or a fatal failure with the propulsion system, what decision is most defendable? And we concluded that we really needed to proceed with the burn.
Latch valves open, line pressure rising.
Normally, the spacecraft is orbiting the Earth, looking at the sky. So, in preparation for the maneuver, it changes its attitude, parts its solar arrays and its high-gain antenna to be out of the way of the thrusters. The maneuver itself is just fire all thrusters for 1 second. And then after that's done, then the spacecraft goes back to normal science.
Verify 1 second maneuver.
Copy. Maneuver complete.
It was a huge relief, a huge weight off my chest. Having done the maneuver and avoided a collision means we continue operating. So continue doing the great science that we have been doing over the past 4.5 years.
So one of the things to take away from this is that that's happening all the time now. Operators of satellites are getting 20 warnings per day, typically, of potential collisions. And of those 20, they know that maybe one is really important, and they focus in on those one or two. But there's so much debris up there now and other satellites that these 20 warnings have to be taken into account. And the reason one of the reasons they get 20 instead of one or two is because they're not really sure where things are. And why aren't they sure? Because the solar wind is always fluctuating enough that the atmosphere is shrinking and growing, and so these satellites are always changing their positions. And they have these essentially giant error bars they carry around the satellite at all times. And so we often talk about the big giant disaster events of space weather, the Carrington events, the power grid going out, people screaming in the streets. That could happen, but it's not likely. But what is definitely happening is that with more and more debris in orbit and with space weather continuing to act as it does, this is getting it to be an extremely difficult job to drive satellites. It used to be pretty straightforward. You just orbit your satellite and check on it every once in a while. Now it's an everyday thing to make sure they're not colliding with something. And it's really, as she pointed out, not at all a small deal to move a satellite. A lot of these satellites have to be in a precise orbit to do their science, and when they move, they have to put them back, and it takes weeks sometimes of interruptions. So that is sort of the day-to-day space weather that is really why we need to get much better at forecasting the solar wind and the atmospheric expansion that accompanies the solar wind. We're nowhere near being able to give these people real small error bars on all this stuff up there yet, but we're getting there. I'm going to go ahead and just skip the rest. This is some stuff on the SOHO, or the SDO satellite. I will, however, end on the largest solar flare in recent history. This occurred on September of 2017, and it's the 14th largest flare on record. And we'll just let this movie play because it's really a beautiful movie of what we're looking at now with the Solar Dynamics Observatory, the highest resolution. Every 12 seconds we get an image of the sun, and now we're really seeing solar flares in the most detail we've ever seen them. So the Solar Dynamics Observatory has been in orbit since 2010. taking pictures of the sun every 12 seconds. It now has 12 petabytes of data at NASA, the largest data set in NASA history. And so the forefront of space weather is now moving into artificial intelligence and machine learning, applying neural networks to this gigantic data set to try and understand these flares and see if we can actually predict them. And that's it. I appreciate you having patience and sticking around a little bit longer than I thought I would. Yeah, any questions?
Yeah, what was the effect on the humans of the Carrington event?
None at the time. I mean, the ground-based, if radiation reached the ground at the time, A, they had no way to measure it. B, it would be slight. And so if you're on the ground, underneath the atmosphere and the magnetic field, you're safe from space weather. But if you're dependent on technology in some way, then that's when you can be affected. So there aren't any medical effects that we know of. Of course, if you're an astronaut in orbit, it's a totally different story. Yeah.
So, sort of following up on your comments about the Apollo 17 close call, there seems to be growing interest again in the possibility of going to Mars sometime. Mm-hmm. And the celestial dynamics are such that there are these launch windows, opportunities every 2 years or so, and you've got your solar cycles of 11 years, which makes that somewhat predictable. Can you say that there are certain opportunities in the future that if we ever do try to mount a mission to Mars, you better not go this time, or that here's a good time?
You know, that's a difficult question because, as we showed, as the solar flares and the sunspots peak, the galactic cosmic rays go down. And so you'd think, well, that's not a good time because there's lots of solar flares going off, but then when the sunspots go away, the galactic cosmic rays come back up. And the galactic cosmic rays are actually more intense in terms of energy than the solar flare particles. So there's not a good window where you can say, now you're not going to be irradiated. The bottom line is you really just have to have a space weather person on board or on the ground talking to you at all times, at least telling you what's going on. And again, the only recourse you have is to seek some kind of shelter in some sort of, thick part of the spacecraft. There are those who believe, and I'm not necessarily one, but there are those who believe that you're not going to survive a trip to Mars. You're going to get cancer. You will be irradiated to the point of not being able to come back if you get there. So it's a very tricky. It's odd though that Elon Musk apparently doesn't think this is a problem.
Right.
It's like there's no. Just handle it. Yeah, in the back.
Do we see the aurora phenomenon on other planets?
Yes.
In a similar to?
Yes. In fact, I'm glad you asked that. There is a really nice set of images now coming off of satellites like Juno and others. This, for instance, is the aurora at Jupiter. This is the aurora at Saturn. So any planet with a magnetic field and an atmosphere will have an aurora. Mars doesn't because it doesn't have a magnetic field. It gets little spots in the atmosphere that they call aurora. But these big, bright ovals and storms occur on all planets with magnetic fields. Any others? Yeah.
If you go back to that the solar cycle graph from a long time ago, it was like one of the first ones you showed.
Yeah.
That had the spikes on it. So it kind of looks like it's growing there, and then it dies back down over time.
Yeah.
Do you have any idea if that's?
No, this is a solar cycle on top of a solar cycle that we don't understand. And back in the 50s and 60s, as we saw in that giant eruption in 1946, the sun was much more active than it has been lately. Solar cycle 24, the one we're just coming out of, was particularly weak. It was the weakest since solar cycle 14 back here in the 1900s. So there are these, it's not the same solar cycle peak every time. There's some sort of other modulation on top of that. Yes?
Is some work being done to help this problem with so much debris up there continuing to get?
There are people thinking about ways to catch it in nets and deorbit it and various. I don't know how successful they're going to be. There's nothing that's been launched yet that I know of to try and remove debris. Debris will eventually deorbit itself as it gets more and more dragged into the atmosphere. It eventually comes down, but some of the stuff that's up above 1,000 kilometers will probably not come down. And so,
And
yeah.
new stuff going up, are they doing anything to?
Now, there are laws that say if you put something into orbit, you have to have a way to get it out of orbit in 25 years. So you have to have enough fuel on board to thrust yourself down into the atmosphere. But it's, as of now, there's about 700,000 pieces of debris large enough to cause major damage. And that's just the things they can track with radar. So it's humans litter, what can you say? Yeah.
Time lag for CME, 14 to 48 hours. If things travel at the speed of light, why is such a difference in the time?
Well, they're not traveling at the speed of light. The photons from the flare are traveling at the speed of light, so we get the flare in 8 minutes every time. But the plasma, depending on the way it explodes, the direction it explodes in, what the background solar wind is that it's hitting, that's what causes the variation in speed of the CME. So it's really a cloud of plasma kind of rumbling along at these varying speeds. And we think that, as I mentioned earlier with the Carrington event, there was a CME that came before the Carrington event because we know there was big aurora. So something came through before the second CME came through to create the really big one. And we think that's a common feature of these big events, is that you get a CME that comes through and clears out all the junk, if you will, and then you get another one that just comes straight into empty space and gets here, in 14 hours. Or maybe even collides with the one in front of it, so you get a big 1-2 punch right away from these 2 CMEs in a row, in effect. So this kind of 1-2 action is something we think is a key to the big events. Yeah?
Maybe we wanted to see something, but then you mentioned that the poles flip every alternate solar cycle.
Yeah.
So does that affect the intensity of the effects on Earth as measured on Earth?
Not to our knowledge.
Second and third one seem to be higher, but obviously the first one doesn't correlate, so.
Yeah, not to our knowledge. The direction of the solar magnetic field doesn't seem to affect the strength of the eruptions or the magnetic directions.
No, if it's aligned, does it have? Is it worse, or if it's anti-aligned, is it worse for Earth?
Oh no, that's a good question though, because what counts is the magnetic field in the cloud, and so the sun's global magnetic field can be one way or another, but those clouds coming off are rotating and doing all kinds of crazy things. So it just depends on what direction the cloud itself is pointing when it hits the Earth as to whether it really connects with the magnetic field or not. Sort of like magnets bounce off if they're pointed in the same direction, so that does count, yes. Yeah.
So if we predicted that there was going to be a Carrington level event in 24 hours, what should everybody do in case? Is there anything in place to make that happen?
Don't rely on your iPhone for maps, and probably avoid taking a polar flight, or if you're about to board the New York to Beijing flight, ask them if they're aware that this could get nasty. And but other than that, again, if you're on the ground and you're not reliant on some sort of technology, you're okay. The biggest risk to society from a major Carrington-like event is a destabilization of the power grid and a blackout, because it's been shown from other blackouts, like the 2003 New York blackout, which was not caused by the sun or a geomagnetic event, but it was a 12-hour blackout, and about 100 people died just from the blackout. So about that, and they've shown epidemiologically studied this, and they've shown that that's about the rate you can expect from a typical blackout. So blackouts are the really bad, dangerous things that can affect people on the ground. But again, that's technology. I gave this talk once up in Montana, and they said, I got a question from the audience, and this woman said, "I'm off the grid. Why do I care?" I said, "You don't. If you're not using any technology at all, it doesn't matter." That's why I had this title for this talk, is why do I care? So yeah, if you're out in the middle of nowhere, you're off the grid, you're safe.
I just had to want to go outside and look up.
Yeah, you want to go out and see the Northern Lights show. So.
How did it get the name Aurora?
That is Latin for dawn. So if you see, as I just recently saw the aurora for the first time myself from a flight from Beijing to Chicago, and we went over the pole, and I was looking for it out the window the whole time, and unfortunately there was no storm going on, so it was very weak, and I didn't see it, and then we were coming into what I thought was sunrise, and I thought, wow, we're really making good time here. And then I realized the sunrise was way up above the horizon, and it was in fact a dim aurora. So it does look in a dim state like the sunrise. And so that's where it got its name. But when there's a big storm, it's really much more dramatic. And yeah, I got all excited. I told the stewardess, "Oh, there's aurora." And she's like, "Dad, it's nothing." they see things like you wouldn't believe up there. So it's one of the benefits of the job. Yeah.
You mentioned the daytime aurora and the nighttime.
Yeah.
And where the reconnection events happen at night in the nighttime.
Yeah.
Is that a normal daily ebb and flow, or is that?
They think that there's sort of always fluctuations in the tail, and that's why you see aurora around the poles almost all the time. And so that diffuse aurora, I think it's still a matter of investigation of what causes the diffuse aurora to sort of sit there all the time. But it's probably small-scale stuff happening all the time. And it's only these big storms that really cause the big reconnections and the big tail rearrangements that really throw particles into the poles and give you the big. In fact, they call those substorms because they come in pulses. As the tail reconnects, it snaps in particles, so the aurora will kind of ebb and flow in a storm, and they call those a substorm.
So do the reconnection events only happen in the tail end, or the?
Yeah, I think there's some in the front too. I'm a solar physicist, so it's I'm a little bit out of my expertise area, but the magnetosphere, I think, does reconnect on the front side too sometimes, and you get particle injections down into the daylight side of the magnetosphere. And maybe that's what they saw in 1921. A very large-scale reconnection as the magnetosphere was squashed backwards. You get a lot of particles, perhaps bright enough to see in the daytime. Yeah.
Do we understand sunspots, like what causes them and why they follow these patterns?
Not as well as we'd like to. We know, that there's some kind of dynamo action. The sun is a plasma, which is an electrically conducting gas, and it's spinning. So anytime you spin electrical conductors, they create magnetic fields. But exactly how it creates this cyclical magnetic field and why sunspots kind of come up in these blobs and then dissipate is not quite known. They think it's basically like a big tube of magnetic field below the surface which floats to the top every once in a while and creates a sunspot. But that's very theoretical at this point. So it's a very active area of investigation in solar physics.
So is SDO a kind of a replacement for SOHO, or is there something else?
It would have been if they put a coronagraph on board. So you can't see the CMEs coming off like you can with SOHO from SDO, but it has this amazing telescope to see the flares and the corona. It has the magnetic field measurements that replaced the SOHO magnetic field measurements.
Is SOHO still operating?
It is.
It is?
Since 1995, it's still up there. It's our last coronagraph, which is why they won't turn it off, because we needed to see these things coming off the sun. But we're really skating on thin ice, because if that goes, then we have no way to see the CMEs. And the only way forecasters can tell you if a geomagnetic storm is going to happen now is by looking at the CMEs coming off in SOHO. Before SOHO, the accuracy of geomagnetic storm forecasting was terrible. Now it's pretty good. They're put within typically plus or minus 10 hours of arrival time, they can tell you. But if that goes away, we're back to pre-1995, and it's going to be rough. Yeah.
When Eugene Parker doing his paper was projected, was that mainly because it was like so esoteric and mathematical and like not empirical enough at the time, or just because of the implications that he made of it?
Both. I think people said, well, there's no evidence for this. You're just making mathematical equations about supersonic flow from the sun, but why would we want to believe that? And there was really no empirical evidence that showed there was a plasma flow, and so it was just soundly rejected that the sun could be constantly. I think people believed there was explosions during flares, but they didn't believe there was a constant flow. And he showed that no, it's constant. It ebbs and flows in terms of speed, but it's always there. And I think that was hard for people to accept. All right. Well, I think one more. Yeah.
So the two instances of the aurora hitting like somewhere near the equator, both of them reported like red lights as opposed to like the typical green that you see in presentations. Is there any significance? That is an active area of research. We think what's happening there is that, again, the magnetic field is getting squashed so far into the Earth by this big pulse of magnetic field and plasma that you're actually getting the Van Allen radiation belts kind of emptying into the atmosphere. And so the radiation belts themselves are getting squashed into the atmosphere and just kind of dumping out radiation. Instead of these nice green curtains, you're just getting a big wash of electrons coming down from the radiation belt. So it's maybe a different mechanism in some way than the polar aurora that we're used to. But I'm pretty sure it does have to do with this extreme squashing of the field
by the CME. So yeah, if you see a red aurora, that's bad. You know? Not good. Right. I guess we'll call it.